Okay, welcome to the 11th practical session. Yes, today we are a bit Christmas themed, but therefore we'll talk about trees. So you will continue to talk about trees.
But that's not all that we have planned for today, right? What else do we have today?
Yes, so afterwards, after we finish our practicals with the trees, which will be very useful for A4, by the way, we'll have our small Christmas quiz planned. Yes, but we won't record this, so this will only be for those who attend today.
So yeah, that's basically what we've talked about already. Some organizational matters at the beginning. First, just a few comments about the assignment 3 interviews. As probably many of you currently were sick or are sick, also some of our tutors are sick, and for this reason we needed to cancel a few assignment 3 interviews. So if also your time slot got cancelled, then you will receive an email within the next few days, and we will arrange a new assignment interview at the beginning of January, so in the first week after the Christmas break. Yeah, we're sorry for the inconvenience, and I mean, we are 16 tutors that do the A3 interviews, and 3 or 4, one it's still a question whether it's sick or not, currently cannot do assignment interviews, so we cannot come up with a solution in this week for everyone. So sorry for this again.
Yeah, and also I think there were also many students that were sick this week, so also for those.
There's the opportunity to take the interview in January then. But now to the new assignment. What?
Yes, so last week we delayed the release of the assignment 4, but today we'll release the introduction videos at 7. Also the upstream will be available today, so you can start working, read through the assignment, you can start programming with your public test cases locally. The repositories I will create on Saturday, so they won't be ready yet, but in 2 days. Yeah, this is just because some additional complexity, because we now have these 2 groups where we need separate things. And yeah, the deadline is on the 21st of January, Wednesday.
Yeah, Wednesday
right,
again.
as always. And we already planned a question hour. I don't think that they are in the videos, the exact date, but we now already have one, so it's the 19th of January. So yeah, 2 days before the deadline in the afternoon.
It should be already in your calendar, so
yeah.
You should be able to see it.
Yeah, and this question hour really is only for some questions that you have or some issues you have with your implementation. You should already be done with A4 at that point.
So even though it's like 5 weeks from now, the assignment is more challenging, way more challenging than the previous assignments. It is also worth 40 points instead of 12 or 18. So please start early with the assignment. If you start in, say, 1 week before the deadline, it will probably not be enough time for you.
Yeah, so it's 40 points, so like A2 and A3 combined. So if you needed 2 weeks for both, then you probably will need 4 weeks for A4 now. So start early, and if you're finished early, then yeah, that's just something good.
Okay, so this is the organizational matters. And then we continue with the example from last time. So last time we talked about trees. So let's see what slides I have here. So we said we started with this binary tree. Like all the elements in the tree were called nodes, and every node then stores some data that you use. So in our case, this was just integers, but I mean, you can store any data there, because you can store an array there, you can store some more complex data structure, whatever you need. And then like the tree property of the binary tree is that every node has up to 2 child nodes to 2 children. And conversely, every node has exactly 1 parent node, except for the root node of the tree. And we also had here an example also from last time. So this would be kind of a tree data structure. So like all these the circles here are the nodes. We store some data in there, which are now the integers, but as I said before, it doesn't really matter. If I take one node, then these arrows indicate that I have children. In this case, it has really 2 children. And for instance, the 7 has 1 child on the right side, but on the left side, it does not have a child. We indicate this by pointing to a null pointer. And if we take one node, if we go upwards, this would be one parent, except for the start of the tree, the root node in the tree. This does not have a parent node. Okay, that's what we have seen. And then we did this example with this binary search tree where the values are ordered in a specific way. So, okay, we start again. Every node has the integer. And we really said one child is the left one is the right one, as an example I've shown before. And the values of all nodes in the left subtree are then smaller than the value of the node that we're currently at. So if we look at the example here, if I take the 5 and go to the left subtree, so if I go here and then consider everything that is below, all the values that appear here are smaller than 5. 1 and 3 is smaller than 5. And if I conversely look at 5 and the right subtree, then all the values are larger than 5. And yeah, okay, the values, that's what I said. And we already had some part of the implementation. And let's look at the code and recap this for one more time. Okay, let's maybe start at the beginning. We had this struct tree node, and the tree node stores some value, this arbitrary data, in this case the integer. We always have the left and the right child, which are pointers because we cannot directly store a struct in there.
Yes. Also maybe interesting is that you can't use the type def in there. So you'll have to use, so you actually need this name that we often omitted previously.
So we have defined this tree node, and then if we go back to the main function, we created the array with some values contained, and then we wanted to insert these values into the tree such that this property from before, the sorting property, is fulfilled. So we wrote this create tree function, and this create tree function basically just iterated over the array. So we iterated over the size of the array, and then iteratively called the function insert sorted to add one more node or one more integer to the tree. And we have already done this function. So we can also look at this function at the very beginning. So basically we always create a new node here, do the null check, of course, the malloc null check, fill in the correct values into the node, and then distinguish 2 cases. The first case was that the tree is empty. So in this case, the tree is just a new node. There was no tree before. Now there's just a single node, which is the entire tree. And in the second case, we had this while loop here. So in this part, we iterated through the tree and selected the correct node where we want to append the newly created node. And then in this last part here, we inserted the node at the correct position. If this is not so familiar to you, then please watch again the last practicals. There we coded this, so I did this together with David last time. Okay, so this insertion part is already done. So really, if we take the tree and insert it, then this works out. Now, there are 2 more things that are missing at the moment. So this function free tree is missing because we allocate the memory for the nodes in this insert sorted function with the malloc, but we have never used any free in the code at the moment. And we also would like to print the tree then in the main function, that we also can view what is contained in the tree. So these two functions are still missing. I think in the last lecture we talked a bit about them, and I will just implement them now, and we'll start with the print tree function. So if we maybe switch to the example, so let's assume that this is the tree, and we would like to print the values in sorted order. So starting with the smallest value, then going upwards to the largest value. And at the beginning, I just know this pointer here to the root node of the tree. How can I now print the tree correctly? We can do this as follows. We know that everything on the left part is smaller, so we need to print all the values of the left part first. Then at next, we print the value of the current node where we are pointing to. And then afterwards, we print all the values of the right part, because they are larger. They should be afterwards if we want to print this in a sorted fashion. Okay, now let's try to do this here.
I think the last coding session homework was very relevant for similar stuff.
Because I think you did something in this direction there. If I want to print this now in the print tree function, I said I would like to print the whole left part of the tree. So I will take the tree that I currently have. So this is in the example, this pointer here. And then I want to go to the left part. So I take the node and also this pointer. So this is then left child of the first node. So this is tree left child. And this is also a tree, because, I mean, if you look at the example here, if we don't think that this part is existing, then the remaining part is also a tree. Same as before, it's now smaller, but it's a tree. So we can also call now the print tree only for this part of the tree.
Yes, because our actual tree pointer is just a pointer to the root node. So everything is just a node. The same if you think about a linked list, then we also don't have really a list struct, but just a pointer to the first node in the linked list.
So we just interpret the number 3 now as the first node in the tree, basically. So we just take the left child of the tree and print the tree of it. Then at next, we said, okay, we now need to print the value of the current node. So now this can be done easily with a printf. So maybe take the value and then add the value of the current node. And then afterwards, we take the right side of the tree. So we take basically this pointer here, take this part of the tree, again, interpret this as an own tree. Don't think that there is anything on this side, and call print tree to this part of the tree. So that's also what we do here. So we go to the right child. So this is now a recursive function, but this is basically the easiest approach to do this. Now there is one more thing to consider. What happens? So basically, let's do this in the example. So we are at this node. We want to print the left tree. Okay, so we basically print everything that is below the 3. Then we again print the left tree. So we print everything that is below the 3, now below the 1. And now, if I'm at the 1 and take the left part here, then it's just null. So in this case, there is no subtree contained on the left side anymore. So in this case, we shouldn't print anything. So we need to check basically if the pointer where we point to points to null, or if it actually points to an active node. So we need to distinguish these cases. And if it points to null, then we need to say, okay, don't print anything. We are at the end of the tree, we don't need to print anything anymore.
Maybe another way to think about it, we said that we now just interpret this node as a new tree. So we just look at this as a whole new tree. And I mean, then we do the same for this. And then if we would still go down here, we would try to interpret this as a tree. But of course, the null pointer is not a valid node. So we can't actually think of it as like a tree.
Okay, how did this happen? So we need to introduce one more thing. So we only want to execute this logic if the tree is unequal to null. So if the tree is kind of empty, we are currently pointing to null, then we don't want to print anything. But if we are unequal to null, then there is something below, and that is what we want to print.
Yeah. So I think you kind of turned it around like you explained it. Because you said something like, okay, if we see that this is null here, we do not want, sorry, you need to switch.
Sorry, yeah.
If this is null, if we are here, if we interpret this as a tree, and we see that this here is null, we do not want to interpret this as a tree and go down here and try to print this. But now we would need two checks. We would first need to check, do we want to print this? If no, we don't need to print this. And if this is null, we also do not want to print this. But we can do it in just one check. Therefore, we just call it with this value, our print tree function. And then if it's null, we just do nothing.
Now, you mean this different. So basically, yeah, we call also print tree on this part of the subtree, but we say, okay, in this case, we don't do anything anymore.
Yeah, so instead of checking before we call print tree, we check it in the print tree. And these two things do the same thing, but we just need one check now instead of two for each child.
Maybe, can I? Yeah, no. Just want to make it large again because this was a bit awkward. Okay. So this now basically prints the tree. Now this is the first time that we can actually execute the program. So maybe call it binary tree.c. Okay. And now if you want to run the program as well, we hopefully see that all the values are indeed sorted, because as in the example before, we do this in the correct manner, and that's why everything is sorted. Now if I execute the whole program with Valgrind, so maybe compile with -g first and then execute it with Valgrind, then we will see, of course, that here we have bytes which are lost, or also here we have 11 allocations or 1 free. If you also maybe write -leak -check equals full, I think we see more concretely that we lose always the bytes, so we have not freed the memory. This is kind of expected. So how do we free the memory? This works now entirely the same as the print function, because also here we say we start at the beginning, we first free the left part of the tree, then we free the right part of the tree, and then afterwards we can also free our node.
Yeah. So why do we need to do it like with the printing? Because if you think about it, we had already the 2D arrays where we had something like, okay, we can't free the array of arrays before we free the arrays in that array. And we have the same thing here. We can't free a node before we freed all child nodes. So and all descendants of that node.
So let's also implement this in the same way. So I think I need to write the function. So free tree also takes again a tree, but it can be also a subtree. Then we check again if we have reached already the last part of the tree, because then we don't need to free anything. And if not, then we free the tree on the left side, we free the tree on the right side, and then we free the node itself. Yeah, so the left subtree gets freed, the right subtree gets freed, and then the current node gets freed. And this then again frees the whole tree. Now maybe check this again. We compile it and run it with Valgrind. Now we have...
I think you did not call the function.
I did not call the function. This is correct. So we should also write call the function at the end.
Oh, okay.
Free tree with the tree.
And at one point you have commented it out.
Yeah, let's look at it later.
Okay.
First compile it again. And now we see, okay, now there are 0 errors and we also have 11 allocations and 11 frees.
Yes. So what, sorry.
Yeah?
Yeah, so what we do here is we kind of free the tree from the bottom up. Because we said we cannot free this node before we free this node. And we cannot free this node before we free this node. So we kind of need to start at the lowest level. And the easiest thing to do again is like with printing, is with this recursive approach where the first thing, if we call free on this node, the first thing we do is we call free on this node. The first thing we do is we call free on this node. The first thing we do is we call free on this. Now it's null. We do nothing. We go back here. The second thing we do is we call free on this. We also do nothing here because it's null. And then we completely free this node. Then we go back. And now we are back one level up in the function call, which in the second function call we do there is trying to free this, which does nothing. And then we finally free this node up here. Then we go up here and then free the second child and go down.
Mm-hmm. So basically we go through the tree in some organized manner, but if we would not do it with recursion, we would always need to remember how to go back upwards, and this is difficult. And with the recursion, we can forget how we go back upwards in the tree.
Or you need to somehow always start again at the beginning and go down into the lowest level, free it, set it null, and then do it again. So it's also possible to write this with loops, but I think the code will get much longer and more complicated.
So, and as you spotted before, there's one more case. So we also, so we free the tree in the main function if we go here, but if we create the tree and the tree is null, so this means that we got a memory error at some point, then we print out of memory return, but we do not free the tree in this case. So let's go into the create tree function, and there I already prepared this last time that we need to free the tree at this point. Why is this now enough? So we start with a tree that is null, and whenever we insert a new node to the tree, we keep the structure as shown on the slide, on the example. It is always a valid tree, like there is always the pointers valid, there will be always a null at the end, so we can always treat every intermediate tree as a tree, because every intermediate tree is a tree. The first tree just points to null, but this is like a degenerated tree. But once we have inserted the first node, it is a valid tree. If we insert one more node, it is a valid tree. It is always a valid tree. It follows the same pattern. And for this reason, if at some point the malloc here fails with the new node, so we create the new node, the malloc fails, the tree that is behind it, so the tree that is existing, is a valid tree. So we can say the tree, everything is fine with it. The malloc returns null. So we return here and then say, okay, everything that we have created so far must be released. So that is why we free the tree here with the free tree function. So this is basically the old tree that we passed to in the insert sorted function. This is then the return value. Similar to realloc, it is either it is a valid tree or it is null. And if it is null, we need to free the tree again. This is very helpful that you keep your data structure in kind of a valid state, in a control state, where you always know how to free it, because then you don't need to think about how to free it in the out-of-memory case, because it always works the same.
Yeah. And I understand if you see this recursive function calls the first time on such a tree structure, it can truly feel like magic that this actually works, like a Christmas miracle or something. But if you have trouble seeing how this works, I think it's really would be a good idea if at home you try to look at our free function or the print function. I mean, yeah, I think both are kind of the same complexity, and just try to play the debugger, draw a tree, and then go line by line through your code, write down what function calls happen and what trees occur, and then you will see that the order that we previously drawn on the tree is exactly the order in which you will visit and free the nodes.
Okay, this concludes the binary tree example. And now we have one more case that we want to cover. So I think we talked about this already. And now we want to extend this a bit. So in the binary tree, as the name suggests, there are at most 2 children. And now the question is, how can we model an arbitrary amount of children for every node? So basically, if we go to the example, maybe go to another site, I would like to have the following thing now. I would like to have a node, some data is stored there, and then it, for instance, has 4 children, yeah? And now maybe this node on the right side, this node has just on the left side is maybe 1 child. This has no child, maybe just indicated again with null. This has 2 children, and this has, I don't know, there's some large number of children. But the important thing is that this amount here, that this is 4 or 2, or some large number, this is not fixed, yeah, when we would like to have an arbitrary amount of children. So this is now the drawing here, but now let's look at a single node and try how we could implement this. So let's start with a node again and assume it has, for instance, 4 children. So let's draw them here. I mean, there are 2 options now. One option would be that this node basically stores an array of 4 nodes. So basically, we would have here, I mark this now outside, that this is basically an array of 4 nodes. So they are consecutive in memory. And this node points to the first element in the array, and we store maybe, so we store basically a pointer, and we also store a size of the array. This would be one option which you can implement. I would like to show a different one. So in this option, we basically always have the nodes in an array. So they are consecutive in the memory. I would like to get rid of this. So instead of doing this, I remove again the array here. And instead, let's maybe move the size a bit. I create an array of pointers. So this is an array again of size 4, and the first element points to this node, the second element points to this node, the third to this node, and the fourth to this node. Inside of the original node, we have a pointer to the array as before. So this is the pointer. And then we store also the size, which is in this case 4. Also, this should be stored in the node.
Yeah. And maybe some value.
And maybe some data. Yeah, let's maybe write this also here. Some data, the reason why we want to use the tree. And I would like to show you this approach now in an example. And I will not kind of construct now a whole tree. This is now getting a bit too involved and too large. But the important thing is not how the tree looks, but the important thing is how we do the setup for a single node. And that is what we want to do now.
Yeah, and then with freeing and printing and everything, you can apply the same recursive principle as we showed you for the binary tree, just that you call the function recursively for all children.
Okay, then let's move to the example. So we again need to start with kind of this tree node, but it will be now a bit different because now we don't have a left and the right child, but we want to create this array of children. So we have a children array. And maybe note now, if we look at the example back, we have here one pointer and then another pointer. So this will be now a double pointer because we need to go one step to the array of pointers and then one more step to the actual node. So we need a second star here. And then we also define maybe number of children.
So this was the size.
Yeah, the size before an example, and this is maybe the data now. Maybe I call it data immediately. Okay, and now, maybe create the first node at the beginning. So we take a tree node. I would maybe call it tree at this moment. I call malloc with size of the tree node. We do the null check immediately. And in this case, we can again, maybe copy this. I'm lazy. Maybe copy this from this example. Okay, so this is now basically the same, but now we need to initialize, of course, the tree node. So like the first node of the tree. So we could, for instance, set the data to 1. Then we could set the number of children. How many do we have in the beginning? In the beginning, we don't have any children. So we set this to 0. And what can we do with the children array? So basically, we could also set it to null. So this would basically mean that in this drawing, we do not have the whole part. There is no array, we're just pointing to null. And this is good enough for 0 children because we don't need to store any children here, any pointers. So we would like to keep it this way. Okay. And now at next, I would like to write the function where we add a child to this specific node. Maybe I should call this node to make it more precise. So we just have a node, we don't have an actual tree. Okay, also here. And now maybe call the function insert child. So we pass the node, and I would also like to pass a data. So that I can fill it into the child. Oh, now this works. Okay, so let's maybe say the data is 2 in the second case. We want to create a node with the value 2 and insert it as a child to the node that we have here. So let's see. Write the function insert child. We get a node and we get a data. And now do this maybe similarly as before, that we first create the new node with the data. If this is successful, then we add it as a child to the node. If this is not successful, we will try to free everything again. So let's start with that. So we create now the new node, which is then the child. Now we do the malloc null check. And if it is null, then we need to return. So probably we should also add some return value. So let's do this, that you have seen this also in the practical ones. We just create an enum, maybe enum return value, call this return value, and then no error 0 and memory error is 1 maybe, and now I can just return a memory error from this part here.
The return type.
The return type also must be adapted, right? So it returns the return value. Maybe should be error code, a better name. And now we can do something like this again. We check if we have a memory error in this case, and if we have a memory error in the insert child function, then maybe call it free tree again with the node. But let's implement this later again, and then we can do something similar as before. Okay, now to the good case. If this worked, now how can we insert the child to the node that we have here? And now we again need to distinguish two cases. One case would be that the node has no children at the moment, and the other case would be that the node already has children. So let's check this. If the node number of children is 0, okay, first case, what do we need?
We said that the children pointer, if we have no children, is also null. So we need to keep this in mind. This is kind of a thing we now established, and we need to always think about that if the no children are 0, the pointer must also be null, and that we do not mix up some states so that it could be something else, because then we will get again hard to debug errors.
So basically, number of children 0 is always related to that the pointer to the children array is also set to null. So I could also write assumption children is null basically. So we need to create now a new array of children of size 1 in this case. So of which data type is this then? Okay, we said this is a pointer, so we need an array of pointers. So should I do this directly here? No, maybe it not. Maybe do it first in a separate variable. So this will be the children. And now this is malloc, size of gnode. Okay, it is 1 star too few, because we would like to get a pointer to an array of nodes. Okay, so we have here the star and here also the star.
So like with the array of strings, we now have an array of pointers.
Basically in the example here, to visualize this, we would like to create now this array. And if we have this array, the data type are pointers. And what do we obtain? A pointer to the first element, so a pointer to a pointer. That's why we have 2 stars. This thing here is a pointer to a pointer, 2 steps here. So that is why we have the 2 stars here. Okay, we need to again do the null check. So if the children array is null, then we will return the memory error, of course. So now we need to keep one thing in mind. When we return from this function, then we kind of do this free tree here. So we free everything that was in the tree before, or everything that is related to this node in this case. But everything that we have temporarily created before in this function will not be freed. So in particular, the child will not be freed. So we need to think about, again, we need to free this resource. We need to free the child. Then this variable that just exists by now in this function gets freed, and then we return, and then we can free everything else.
Yeah, so if the child was already in the tree, then we would not need to free it because the free tree does everything. But we currently try to add the child to the tree with this malloc here, and now this fails, so we didn't add the child as a tree, so we need to actually free it again.
Now post if it works, then we can add the child to the tree and bring this the tree again in a valid state. So we can now say the following to the current node, the number of children is now exactly 1. The node children is now this children array, and the node children at position 0, the first element should be the child. And then we can return with no error. All this worked out now. Yeah? So this is, we really set everything. We need to update the size accordingly. It must be always the right size. Otherwise we get in trouble. We need to set the array, of course, to the allocated array of 1 element. And then we also need to set the child at the position. I did one mistake in this case. We have never initialized the child. And this would be now a big problem, because now if I move back to the drawing, if I do not initialize the child, so this would be the child, and if I don't initialize it, what is then basically the size of the child? It could be some arbitrary value, so I don't know if I iterate over the tree. What is the pointer? It can point to something. You always need to initialize it. So this would have made an error.
So this would already be an error because we tried to call free tree, and the free tree will walk over all childs and then try to free it. But if our child now has some garbage value as a pointer, we'll try to free this also, and then we'll probably crash or something different will happen.
So always make sure that everything is initialized. In this case, we set now the data correspondingly, the number of children, and this array should point to null, that we know there are no children, and also these two are correctly set together.
But clog would also have worked.
Except for the data,
Except for the data, yes.
Okay, so we've covered the first case, that the number of children is 0. Now there is one more case, namely the case that the number of children is larger than 0. So I can also write now this assumption that children in this case is valid heap pointer to some array. Yeah, because there is this one child, so this pointer points already to some array on the heap. Now how can I continue now? Now I have some array on the heap, and I would like to increase the size of this array by 1. So we can use realloc in this case. So now use everything that we have learned about realloc. So we again get this data type, then maybe call this again children. So note that this we want to increase of the node element, the array. This is a fresh variable, so this serves as a temporary variable for the realloc.
Maybe call it temp children, so it's really clear.
Okay, temp children. Maybe I also want to do it then here, even though it was not necessary here, but
also an check.
And now I call realloc on the node children. This is the children array. I would like to increase this. So I take node number of children. This is the current size. I increment it by 1 and multiply it with the size of a tree node pointer, which is the data type which we stored there.
Yeah, really important to put the parentheses around the multiplication here.
Otherwise we'll get some awkward number here. So we get one more element. We would like to reallocate the old children array, and we obtain a new variable such that if the realloc fails, we can still access the old array and free it then. And now we do need to do the null check. So if the temp children is null. So what happens if the temp children is null? We could not increase this, but then realloc doesn't touch this, the old array. The old array still exists, it's on the same location, the pointer is still valid. So basically, the whole tree, and in particular the node, is still valid because it has a working array to children, this was not changed, and we have also not changed the number of childrens at the moment. This is also the same as before. So basically this realloc doesn't do anything to the tree that we currently have. And for this reason, the tree that we have is still valid and well structured at the moment.
Maybe if you go to the visualization. So
Yeah.
what we're trying to do with the realloc is like increase this array here by 1, and we want to add a new pointer to a new node. But the problem we have now, this realloc, where we increase this here, now fails. So it is never increased. But this is still a valid state for the tree because we did not increase the size of the children in the code yet. So it's still 4, and this array with the 4 pointers here is still valid.
Mm-hmm. So for this reason, if we return now with a memory error at this point, the tree is in a nice state, and if we call then free tree, everything is fine. Yeah, we can free the tree as usual because everything is in a nice state. So we can then make this call. One thing is missing, it's the same as before here. In this function, I mean the realloc failed, we don't need to do anything here, but we did the malloc at the very beginning with the new child. We need to free the child, of course, before returning. So we free the child at this point.
So we kind of have a situation like, if you
Yeah, sorry.
So we kind of have a situation like this, that we have a pointer to this child, but we did not insert this pointer yet into the array, and increasing this by 1 here failed. So we also need to free this here because this is not in the array yet. Mm-hmm.
So the goal is always that everything is in a fine state, that we know what is there, that we can easily free it. Okay, and now if this is working, what can I do now? If the realloc worked, I can just update the node correspondingly. So in the node, the number of children is increased by 1 because we called the realloc. Then we need to set the children array to the new array. And then we need to insert at the last position. So this is the node at number of children -1 to the index. Since we index with 0, so at the last position, we set the new child. And now the child is contained in the tree. And if we would free now the tree, then we would also free the child. And now we can return with no error.
Mm-hmm. So if you go to the visualization maybe,
Yeah.
so that we have the final image, the reallocation worked, we have this new element, and what we do is we copy this pointer in here. So we now have a valid pointer to a new node that is in a valid state, and of course the children of this node we already set to null. So the tree is again in a valid state.
So everything is fine now at the moment. Now maybe I just copy this over again. Maybe do it with maybe 3 here. We just enter a second child to the node, and maybe also a third child, which gets the data 4, just to make it a bit larger. And maybe compile it, and then maybe also see whether this works. Arbitrary tree.c, I mean with -g, I just execute it, but it will not print anything because we've not printed it, but at least it doesn't crash the program. And let's see whether I can run it with the debugger. I tested this, so I hope it will work. Okay, it will work, but I should probably set something here. So if we are in insert child, and now maybe I step over once, then the node is some pointer to some address. Maybe I should increase it a bit. So the node is some address, there is some data, the value 1 contained, there is one child, and this children points to some address. And if I would, can I make this smaller? No. I can. Okay. And then this children is an array. If we dereference it, we again get a new node, which has the data 2, which has 0 children, and a null pointer there. If I would like to watch now children at 1 and at 2, I could also add this here, but I will not do this now. But you can also watch this in the debugger, that this is kind of the right structure that we have described. Maybe go over this on your own again. This was a bit fast now. But it is there. So last thing, we also need to free it now. We would like to call this free tree function here, 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 and at the end. Free tree with the whole part. Now we also need to implement this function here. So free tree, and it will just get a tree pointer tree. Yeah, okay, let's do it like this. Now again, if we look at the visualization, we again need to do this in a recursive manner. So you would first, so we start at this node, then we need to first use this pointer to go to the array. So we cannot free the array at the beginning because then we cannot go further. Then we need to free the children. So these 5 children. So let's say I free this child, this child, this child, and this child, and everything below. Yeah, there could be some other children again, but okay, we don't draw them here, so we free everything here. Once we have done this, we can also free this array. And when we have freed this array, we can also free the node. So this will always be the same sequence. First free all the children, then free the array, then free the node. Also again, bottom up, because if we free the node first, then we do not know where the array is. Or if we free the array first, we don't know where the children are anymore.
And of course, for the children, the same thing. We cannot immediately free the child node. We need to call our function so that it actually frees our children first.
So also let's implement this one. So we said free children recursively. And this is now just a for loop. Yeah, I will write now I'm sorry.
What, maybe child index?
Let's write child index. Yeah, child index, proper variable naming. How many children do we have in this node? So child index less than 3 number of children. Child index plus plus. So now we call free tree on the tree. Then we go to the array, to the children at the respective position. So note that we do not free the node immediately. We free, but we call this function recursively as you described before, because also this child node could have something below. So we call this function recursively. Then we also need to free, and now we can do this with a actual free the array. So 3 children. And then at the very last step, I can also free the node itself. So I can also free the tree. Okay, now maybe write the comments here. Free the array, children, free the actual node. Okay, so this frees the children recursively. So we iterate over the children, free them all, then we free the array, and then we free the actual node. Now, yeah?
I mean, I think I have a question for the audience. I don't know if you wanted to do the same thing.
Please ask.
Do we need to check if the children array is null here when we free it?
Basically, we have the same cases again.
Yeah, if we go to the visualization, do we have a problem if we are trying to free this node and the children's are null? Maybe go back to the code. Because here we are accessing the children, and maybe if this is null, we could have a problem.
Yeah.
Also here we're trying to free it. Maybe do we want to vote?
Yeah, okay.
Okay, so who thinks that we still need to check if the children's are null and only then try to loop over the array and free it? Okay, who thinks that this code is enough and we do not need to check for null with the children? Okay, many more think that this is enough.
Okay, then let's see why it might be enough. So this loop iterates over the number of childrens. And if the pointer is null, this children pointer is null, then we said, because we were like precise programmers, that in this case, although the number of children must be null. So this for loop iterates as long as child index is less than 0, but it starts with 0. We do not perform any iterations. So we will never access the tree at children. So we will never access this null pointer. So the loop is fine because it will never be executed if there are no children. And then here at this point, free the array of children. If the tree children is null, then we know from the lecture that freeing a null pointer doesn't do anything. So also in this case, nothing happens and it is fine. And then we afterwards free the tree, and this works then out because, I mean, we know that this tree exists.
But for this to work, we really always need to make sure that if we call the free tree, then the number of children, if we do not have any children, then always the children pointer must be null and the number of children must be 0. We can never introduce something like the number of children is 0 and the children array pointer is just some garbage value. We really need to ensure that both is always the case for this to work.
But there is one thing. Now if I go back to the binary tree code, I wanted to close it. If I go back to this, in the binary tree code, where was the free? Here, we checked whether the tree is unequal to null. And now it depends if we say that an empty tree is valid as well. Because if a valid tree would be empty, then the tree could also be null. But then we would access tree number of children, 3 children in these two cases. So it probably would be better that we add here that we only execute this if the tree is unequal to null.
Yeah, so we do not need this if we always just call free tree on something that is not null, but maybe this check is better in case you want to, because the free does nothing if we would try to free null, and so it might be better that we imitate this behavior that our free tree also does nothing if we pass a null pointer to it.
Okay, and now I give it one last try. So we called the free tree everywhere. Now let's run it. Now I'm in the wrong one here. Let's run it again, compile it. run it and then run it with Valgrind maybe. If we run it with Valgrind, we see now there are 7 allocations, 7 frees, and we called the print tree function at the very end, so we did the correct memory management.
Free tree.
What have I said?
Print tree.
The free tree function at the very end. Okay, so this really works out. So this is now kind of the important part where this function insert child. And now if you construct such a tree, and if you want to insert a new child somewhere, I mean, you need to find the correct node where you want to insert something. But once you have found the correct node, then you can just call this function insert child and it will do the right thing. So even though we, in the main...
I think it's the same like with the binary tree, where if you want to insert the sorted, you first found the correct node and then inserted the value at the left or right. And now you also need to find the correct node and call insert child. And
then this works for any tree basically. So this is not a simplification or a large simplification that we just started with a single node, because if you're in a tree, you find the correct node and then apply the same operation there.
Yeah, so I think this is already a full tree implementation basically.
Actually, yes, yeah. Okay, I think it was challenging, but it was important for assignment 4, and that's why we wanted to do this. So now maybe are there any questions regarding the trees? Otherwise, we would now make a brief break for approximately 5 minutes, and then we start with the more fun part with the quiz that we have prepared. So let's continue in 5 minutes at 16:38.